So for the last example of a tree diagram and for that alternative, I wanted to show you a real life example. So this is from a book called Calculated Risks. This guy went and did a study where he told doctors in both Germany and the US the following. A woman in a low risk group, age 40 to 50, with no family history of breast cancer has a positive mammogram. What is the probability she actually has cancer? So he gave the doctors more information than this. He told them the probability the woman in this low risk group has breast cancer is less than 1%, it's 0.8%. If a woman has breast cancer, the probability that she'll have a positive mammogram is 90%. So positive mammogram with breast cancer, so that's a true positive, is 90%. And if a woman does not have breast cancer, the probability she'll have a positive mammogram is 7%. So there's a 7% false positive rate. And again, they asked the doctors, what is the probability that this woman with a positive mammogram actually has breast cancer? So here were the results of the study. 25 German doctors estimated this probability, and their estimates ranged from 1% all the way up to 90%. If you recall, 90% was a chance of just having a positive mammogram if you had breast cancer. And hopefully we realize there, the if on that one is if they have breast cancer versus right now we know if she has a positive test result. So those doctors were conflating those different conditional probabilities. So 8 of those doctors said 90%. They went with that value that we were talking about of being just way too large. 9 of the 25 doctors said it was somewhere between 50 and 80%, and 8 of the 25 said that it was 10% or less. So American doctors, they did even worse. 95% of them said it was somewhere around 75%. So they all said this woman had a very, very high risk of having breast cancer. So let's figure out the actual probability. So we're going to go ahead and calculate this ourselves. And we're going to do it first with a tree diagram and then with an alternative. So here are those details again. We were told that in the high-risk group, only 0.8% have cancer, 90% of people with cancer had a positive mammogram result, and 7% of the people without breast cancer still had a positive mammogram result. So if we wanted to set this up as a tree, we would be using the actual true percentage of having cancer as our first splitting point, because this was positive given cancer and this was negative given cancer, if I want to use probability notation. So this was just the probability of people in this low risk group having breast cancer. Note all of this is in the population of this low risk group of 40 to 50-year-old women without a family history. But we don't need that as a conditional because that's just our population that we're interested in. So if we were going to make a tree diagram with this, what we would do is we'd say, okay, we have all of these low risk women, right? They fall into one of two categories. This is going to be that they have breast cancer or that they don't have breast cancer, right? They're cancer free. So we know that this probability is 0.8%. Oh goodness, we should express that as a decimal. It's 0.008. Very, very unlikely. This is why they call it the low risk group, right? And if we wanted to, we could even put probability notation on this. I don't feel that strongly right now because I'm just trying to show us how this works. So for not having breast cancer, then, well, that's everybody else, 99.2% or 0.992, because these have to sum up to all the people in our group. All right, and then our second split, oops, I wanted to use blue. Of the people with breast cancer, there's two options. They could have a positive mammogram or a negative mammogram. We know that they have breast cancer. We know that they're in that group in this particular example, right? So we could figure these out. Probability of a positive, well, this were a true positive, so 90%. Probability of a negative, well, that would be the other 10%, right? And then we could multiply down these. And the same thing for the no breast cancer. They could have a positive test cancer, a positive mammogram, or a negative mammogram. And they told us that there were 7% false positives, which means that 93% of them must have come back negative as a true negative. So we could obviously keep going, plus and breast cancer. negative and breast cancer, positive and no breast cancer, blah, 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 and negative and no, by just multiplying these across. So, this probability is going to get super, super small. Looks like we're looking at 0.0072, which leaves us as 0.0008. I need a calculator. Fine. I will do this with a calculator. The next one, we were dealing with 0.992 times 0.07. Just like before, I'm just multiplying down the rows, right? Down the branches. And so we get 0.06944. I'll just round that to 4 decimal places. And that 0.992 is then times 0.93, which gives us 92.26. All right, and so remember the original question. The original question was, if we know all of this, what is the probability? What is the probability if somebody already had a positive test result that this person has breast cancer, right? That was the question that was asked of these doctors. And we know that this is going to be as simple as finding breast cancer and positive over all of the positives. And of course, we can make our contingency table and do all that jazz. We have breast cancer and positive. We know our numerator. And we just need to figure out what the probability is of all the positive people, which if we made the table, will be these two added together. So I want to show you an alternative because I think it's really, really slick. And for those of you who are sitting there going, why are we multiplying these things together? I don't get it. This is a great alternative. If you did this instead of the tree diagram, I would still give you like 4 of the 6 points because you've made a valid, display. So here's the way this display works. We're going to just start with our best friend, the contingency table. Bloop, bloop, bloop. And we're going to go ahead and put in our 2 different events that we have going on. We have either the person has breast cancer or not. And we have either a positive or negative test result, right? We always like to have these so that they total up to 1. So we have the thing and its complement. And then we need to make sure that our events overlap that we need to overlap. So the other piece of this puzzle is that we start with a hypothetical 1,000 people. There's a hypothetical group of women from that low risk group, right? We know that 0.8% of the women from this group actually have breast cancer, according to those probabilities that are given to us. So we know this is 0.8% that actually have breast cancer. And we could multiply those together and we'd find that 8 of the women in this group then have breast cancer, which means the other 992 must not. And then that's when we start using that information about the false and negative, false positives and true positives, right? We were told that of the women with breast cancer, 90% have a positive test result. So that's about 7.2. We'll just round that to 7. So it means 7 of those 8 women will have a positive test result, while 1 will not. All right, and in the no breast cancer group, we were told that there was a false negative rate of 7%. 7% of them would still have a positive mammogram, leaving us with about 69 of these women having a positive test result despite not having breast cancer. And then our last group, that would be everybody left over here, which is 923, I think. And we could even add these up and figure out what these other totals are. So 76 and 924. All right, and now the original question is, I think, a lot easier, right? Somebody had a positive test result. What's the probability they have breast cancer? And now we can do this thing intuitively, too. We don't even need the formulas. We can just say, okay, we know that they had a positive test result. What's the probability that they actually have breast cancer? So we're just looking at 7 out of the 76, which is less than 10%. So remember about those doctors, right? If we go back to the doctors, I moved my thing, I forgot. I don't even know if I can move it. It gets mad. Remember back to our doctors. only 8 of the 25 German doctors said 10% or less, where less than 5% of the American doctors said that. So this idea of these probabilities and the conditional probabilities really truly matters, especially based on what you originally started with.